The fundamental theorem of algebra states that a polynomial has the same number of zeros as its degree. So if you look at this very simple question, how many zeros does this function have? All it's asking you to do is look for the degree of the function and say that's how many zeros it'll have. So if you have f of x equals x to the fourth, how many zeros will this function have? 4. And that's literally all this question is asking. It's just a test to see if you can recognize that the number of zeros will be the same as the degree. Now we're going to launch into actually exploring those zeros, some of their characteristics. So when you're finding zeros, some zeros may be repeated. So in this function, we're expecting to get 3 solutions, right? Because it says x to the third power, that's our degree. But 2 of them may be repeated, so let's see what happens. You should always look first to see if you can factor it. Now, if we tried to factor this by grouping, you should notice that what you take out from the first bracket and the second bracket is not going to get you the same thing. So it's not going to really work in this one. When you can't factor, that's when you resort to using P over Q and testing all your choices. So if we set up P over Q for this problem, our factors of our constant term, which is 48, there's going to be a lot of them. So the factors of 48 include 1, 2, 3, 4, 6, 8. I'm going to put a dot, dot, dot here because this list keeps going. It's a fairly long one. And if we can find one of the ones that works lower than 8 here, then we don't actually need to list out all of those other ones. And the bottom of the fraction is just plus or minus 1. So we're dealing with whole numbers here. And hopefully we'll get lucky with one of the ones we've already put on our list. So let's just pick a number to start with and test. How about positive 4? We test that in synthetic division here. We use 1, negative 5, negative 8, 48. Remember that we're looking to get 0 as our remainder. And if we get 0, that means positive 4 is one of the solutions. So let's see what happens. Bring down the 1 and multiply, add, and multiply, add, and multiply. And sure enough, 48 minus 48 gets us a 0 as our remainder. So x equals 4 is one of our solutions. And I'll put that over here so I don't forget that I've already got it. Now I've got a new depressed polynomial. I could either keep doing synthetic division and use the guess and check method, or I can see if this is a factorable polynomial. So let's write it out. Used to be x third, so now we're x squared minus x minus 12. If you look at that trinomial and see if you can factor it, it looks possible for this one, so we're in good shape. We're looking for what makes negative 12. That adds up to negative 1. You should be able to figure out that that's going to be minus 4 and plus 3. So now we're going to come over here and fill in the rest of our zeros since we can see what they are. One of them is going to be x equals negative 3. Put a box around that. And the other one is going to be another x equals positive 4. So you notice that 4 that we got from synthetic division, and there's another 4 that we got from after factoring, has to count twice in order for the fundamental theorem of algebra to be true, right? We were expecting 3 answers, and technically we did get 3 answers because we're going to count that 4 twice. Another thing to know about zeros is that some of them might be real numbers, but some of them might be imaginary, and imaginary answers count as well. So for this polynomial, we're expecting 3 answers, right? We have it x to the third power as our degree. So we're expecting 3 solutions, but they may not all be real numbers. So always look first to see if you can factor. If you can factor, that's always going to be the fastest way to do it. So looking at our first 2, if we take out an x squared, we'll be left with x plus 5. Looking at our second 2, if we take out a positive 4, we'll be left with x plus 5. So factoring works in this example because we got the same thing twice. So let's bring down that x plus 5, and in the second parentheses, we'll bring down that x squared plus 4. Now from both of these, we can get our zeros by setting up 2 equations. X plus 5 equals 0, and x squared plus 4 equals 0. In this equation, x is going to equal negative 5. Nice and easy to solve, good linear. This one, if we subtract 4, you'll notice that x squared equals negative 4. Now we're not done because we have to square root that x so that we can get x by itself. When you square root, remember to take the plus minus square root of both sides and anytime you have a negative inside your square root sign, this is when you get I, right, an imaginary number. So x is going to equal, the square root of 4 is 2, and we've got that negative inside of there. We have to remember to put an I next to our answer. So we will have x equaling plus or minus 2I. We'll put a box around that answer. So counting up our answers here, we have one real answer, that's -5, and we have two imaginary answers, right? Positive 2I and negative 2I. So sure enough, we got 3 answers like we were expecting based on the fundamental theorem of algebra. And then there's this one. The little note on top says more zeros, more work. And that's just the truth of it. If you look at this function, the highest exponent is a 5. You know you're expecting 5 answers, and you're going to have to do that much more work just to get your 5 answers. So let's launch into it. There's no way we're going to be able to factor such a long polynomial. So if we can't factor it, we're going to jump right into P over Q. It's the only hope we have for finding some zeros that work. So our P, factors of the constant term, include plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. And luckily, our leading coefficient is a 1, so we don't have to worry about testing any fractions here. So let's start by testing maybe -1. Maybe we'll get lucky with the -1 and see if it works, okay? So our coefficients are, and there's a lot of them here, 1, -4, 4, 10, -13, -14. Let's do synthetic and hope that this one works. We're looking for 0 as the remainder. So bring down your 1, then multiply, then add, multiply, then add, multiply, then add, multiply, then add. It's looking good. Multiply, and yes, we got 0 as the remainder. Okay. So we have one answer that definitely works, and that is x equals -1. I'm going to write it over here so I don't forget I found it. Now, if I tried to fill back my x's into this depressed polynomial, I would still have x to the 4th power as my highest one. So there's really no point in filling in x to the 4th. I'm probably not going to be able to factor it anyway. Why don't I just do synthetic division again with my new coefficients? So I'm going to take this line of coefficients, the one for my depressed polynomial, and set up a synthetic division problem with those. If they work in the original problem, they've got to work in this as well. So since it's a little bit shorter, I'm going to use these as my coefficients. And I'm going to check -1 one more time, in case it happens to be a repeated 0. If you should remember from a couple slides ago, we had that repeated 0, it counted twice. So what if -1 happens to count twice here, right? Let's try it a second time and just see if it works again. I'm going to extend the page a little bit so we have some room. Let's see if -1 works again. All right, bring down the 1, multiply, add, multiply, add, multiply, add, multiply, and we get another remainder of 0. That means I have to put x equals -1 on my list of answers a second time. So we've got -1 as a repeated 0, okay? It's counting twice. We've got 2 of our zeros, but we still have 3 more. That's why this is such a long problem. So I've got my new coefficients down here. I could fill my x's back in. I would still have x to the 3rd power, though, and that still wouldn't be factorable. So since I'm going to have to use synthetic division again, I'm going to use this shorter version rather than the original ones, because if it works here, it would work in the original one. All right, so here's my new coefficients. Now, what to test in the box? So I've already tested -1 twice. I'm not going to test it again. I'm going to try to test something else from the list, okay? So you may have to go back up and look at your original list, your P over Q, and pick something else to test. So we've already done -1. I'm going to try +2. Let's see if +2 works. I'm looking for another real answer this time, okay? If +2 works, then finally we will be down to having an x² polynomial, which would be great. All right, so let's try +2. Bring down the 1, multiply, add, multiply, add, multiply, and we get 0 as the remainder. I'm getting lucky with my guesses here, okay? So sure enough, +2 also works. Let's put that on the list. X equals +2. Now I've got -1, -1, and 2. That's 3 of my solutions. I still got to go for my other 2 solutions. So now I'm down to just having a nice x² polynomial, so I'm going to fill it in. x squared minus 4x plus 7. And I'm going to look and see if I can factor that. So does anything multiply to positive 7 that adds up to negative 4? Not that I can think of. So if we are stuck at the end here with a quadratic equation, we can't factor it, we're going to have to use the quadratic formula to get our final two solutions, okay? So the quadratic formula with this set of coefficients is going to say x equals negative b plus or minus the square root of b squared, which will be 16, right, minus 4 times a times b all over 2a. And then we just simplify so that we can write our final answer as nice and simplified. So 16 minus whatever 4 times 1 times 7 is, which is going to be 28. So 16 minus 28, which will be negative 12 over 2. To simplify this even further, let's deal with that negative 12 under there. So x is going to equal 4 plus or minus. We know we're going to have to take out an I. We're also going to split that root 12 into a root 4 root 3, right? Because 4 has a square root, and we can simplify that. So the square root of 4 is 2. So instead of writing plus or minus here down the square root of 12, I'll write plus or minus 2i square root of 3. And this is still over 2. And finally, I simplify my fraction if I can simplify all three of these by the same thing. And I can divide them all by 2. So this will become 2 plus or minus I square root of 3. And these are my other two solutions. So the answers to this polynomial, which was x to the 5th to begin with, we had negative 1, we had negative 1 again, we had positive 2, and then we have 2 plus or minus I square root of 3, for a grand total of 5 solutions, which is what we were expecting.